But anyway, so Ondřej has been working on dialogue systems, and an interesting aspect of dialogue systems very often is to generate human language. So in that sense, he shares a little bit with the content of this morning's lecture, where people who think of translation think about extracting the meaning and then generating text in the other language. But Ondřej is going to focus on dialogue as text generation in a different context, and he's going to tell us more about it. So, all yours.
Okay, thanks so much for the nice introduction. So hi everyone. So let's see if this works. Yeah, perfect. So I'd like to talk first a little more about transformer models and large language models and stuff like that you probably heard from Ondřej. You probably heard it several times this week already, but I'm sorry, I'll try to basically show you some of my points on that, and in the second half of the presentation, I'd like to go specifically into dialogue and generation or text generation, and a little bit into evaluation as well, which basically Ondřej prompted me to add to my presentation, so I just put it in this morning. So I basically just start with a general introduction on transformers. I guess I'll be a little more high level than Ondřej, but generally you probably already saw that we have some subword representations, some subword embeddings, and we have these transformer attention blocks and fully connected layers that are somehow processing the input, and the main thing that transformers do is predicting the next token or the next subword. And essentially we can just take the network, the shape, initialize it randomly, and iteratively improve. I suppose what you saw also partially in the morning, even though Ondřej was mostly focusing on the encoder-decoder transformer, there are several variants of the network, and in the encoder-decoder variant, which was the original one designed for MT, that basically takes a text, encodes it into some vector representations, and these are then attended to by the decoder, which decodes some output word by word. But that's not the only option. You can also just have an encoder where you just build a representation of the inputs, where you just try to represent some piece of text or some kind of a sequence. And these models usually are good for some kind of text classification or this kind of tasks where you put a classification layer on top of the whole model, and you have very nice representation of the whole input. So that's encoder models, and what I'm going to be talking about probably most of the time, or I'll mention basically all of these, but most of the time I'll be talking about decoder-only models, which kind of do the same thing as the encoder-decoder models. It's just that you just they just work left to right. They just technically just decode, but you can also input stuff by just inputting things and ignoring what the model would generate. So basically, you just add in a prefix. I'll show an example in a second, and that's actually what the shape of the most LLMs currently is. So they're basically transformer decoder only models. Now, if you look at the model in kind of a little more detail, and this is as far as I will go with the detail, we start with these word embeddings. So we have some numbered, list of numbered subwords, and each of them is assigned an embedding, which is basically a couple of hundreds of floating point numbers, and we can just feed that into the model, And you can also see that there's a positional encoding added to the embedding, which is essentially another vector of a bunch of numbers. And then we have the individual transformer blocks, which always start with an attention model, and there's some fully connected layer that basically mixes the data up in a way. And you have multiple layers. I'm only showing 2 because that slide would be too tall otherwise. But you have a whole bunch of these layers, and at the end you typically, or this is the decoder model, you would have a softmax classification that goes again over the over all the subword tokens, and you can see that you get a probability distribution. And this way, you just predict the next word, and you can feed that word back and pass it through the whole transformer, and then get the next word, and then feed it back again, and then you can generate the whole text essentially token by token or word by word. You can kind of imagine that this transformer has been trained to predict some weather forecasts. So it's kind of how transformers would operate, at inference time. And when you use these decoder models for, basically anything, you usually don't just want to, start generating from some kind of a starting symbol and then let them generate random stuff. You can also just feed in some information. Let's say that we feed in the actual weather, and you ignore whatever they produce at the end. They can just use that information when the attention model is attending over the input sequence. So so basically, this is prompting. This is basically you can just feed in stuff into the model. It passes through the same layers. It does everything exactly the same. The thing is, you don't have to always feed back in whatever is the most probable output predicted by the last word classification or token classification layer. So you can actually feed in data even into a decoder model, and that way you kind of have like a makeshift encoder-decoder model, if you will. And this is basically how most transformer models get used today. So you feed in some stuff, you ignore what it would predict, and at some point you just start predicting the continuation of that text. So that's kind of how it looks like at the inference time. And I said, kind of already mentioned that you don't always have to you don't always have to predict or feed in. In here you can say that we fed in the most probable word according to this classification, but you don't have to do it all the time. So there's a whole bunch of decoding algorithms that you can use with these models, and now it's a question like what algorithms do we have, how we can use it. Obviously, maybe we would want to have we would want to generate a sequence maximizing this. Let's say that this X is whatever we are feeding in over here, and here is our Y that we want to generate, right? And now, I'm saying on the slide, this is not technically possible in practice. Do you know why this is not possible in practice? To just generate the globally optimal sequence. Yeah.
Because it takes too much processing power to figure it out.
Yeah, basically. So there are just too many options, and it's kind of hard to find that sequence. So we have some approximations which I'm going to go into a little bit. We have some we can do greedy search, we can do beam search, and we can do some kind of sampling, and there are some additional tweaks to that. We can, for instance, want to decrease the probability of like repeating the same tokens over and over, so that the model doesn't get stuck into like a loop repeating itself. So if we look at the greedy search, which is one of the most commonly used approximations, the idea is that we go this way, and we always take the most probable word at each step. Now, why this is not optimal? Why doesn't it always? Why doesn't this get us the optimal sequence? Yeah.
You have many potential paths because. Well, I think you have the example there that it's just there's sort of certain ones that are just like too overrepresented ones, and so you might need some other least likely paths with the pros of an optimal result. So I guess you're gonna go for beam search to explain that. But it's
Yeah, exactly. So we basically can overlook, some paths just don't look so probable at the beginning. And you can have a place where I don't know, like one of the paths would be less likely. Let's say over here, I don't know, you could get the car, and then if these things have higher probabilities, eventually you might you might get over the probabilities of these things that are more probable, and that's exactly the example which basically, says you would want to say something like this: cake tastes great, and the model would generate this is, and then it probably can get something like okay or stuff like that, because there's a lot of examples in the data that start with this is, and there's like no way of coming back. So that's greedy search. Yeah, and as you said. Kind of the solution for this, or a solution for this, is beam search, where we always try several continuations, and we always try to keep essentially like a beam of k best hypotheses or k best partial generations. And that means that we always produce like a bunch of outputs, and this gives us the option also to pick a better output afterwards. So even like after we finish generation, we can do some stuff with that. We can do some re-ranking. This is just an example of re-ranking that I did ages ago in my thesis, where I basically had the model generate a whole bunch of stuff, and then try to pick outputs that matched the inputs, basically to in a dialogue. I wanted the dialogue to make the dialogue system reuse the same words as the user would be using, because this is what people do. So that was just like an example, but you can do re-ranking based on any criterion you choose. So that's greedy and beam search, and the alternative, and this is actually what is used quite often nowadays, is sampling. You can obviously just take the probability distribution predicted here, and sample from the distribution instead of just picking the maximum, and that's great. The problem with that is that like the distribution has kind of a long tail, and there's a lot of different tokens that are kind of almost impossible to generate, but there's so many of them that you're quite likely to hit some of these improbable tokens that probably will not make your output look better. And this is why the most used sampling algorithms have something like some kind of a limitation on what to choose. So the idea here is that we have just a few options. So that's in top K sampling we just say, okay, we just choose from the top K tokens that are the most probable ones. So this avoids this long tail distribution. So instead of choosing from the whole distribution with this long tail, you just ignore that bit, and you have you recompute the probabilities, and you have a choice of some reasonable tokens. So that's the idea here. There are some variants on that. There's also a top P or nucleus sampling where we just try to find the. Oh yeah, I kind of misrepresented the pictures, I guess. Yeah, because like here, yeah, you would always like kind of in both cases you kind of this, and you can kind of see here that in this case. You basically just remove like 1% of the probability mass, and in this case you remove much more. Actually, you remove like something like a third of the probability mass in the case where the model isn't so sure. So a compensation to that could be the nucleus sampling, where you always say, okay, let's say, we always want to have like a 90% of the probability mass there, and we just choose based on that. And here you can see that, you have quite a few choices to cover this 90%. In this case, it's just three words. So it's really depends on the situation. Of where the model is in the generation, but you can use these types of sampling. There's also epsilon sampling, where you just kind of cut everything like below a certain epsilon. There are more variants to this, and you can also adjust this, and you can make the model either like more conservative, as in here. Sorry, I don't know why this is not picking up. So you can see that this is like more conservative than like the basic situation, or you can make it like a bit more free, a bit more volatile, and this definitely influences a lot of the text. There's also kind of a question to all of this, and this is what my postdoc Zdeněk, who actually built these nice pictures, who found this recently, and it's a kind of a good point that I don't know how often you would use these different samplings and how often you would play with this with LLMs. I'm not sure. I'm also not doing it as much as I used to. So there's kind of a discussion as to like whether these are still useful, or whether like LLMs kind of solve everything using greedy search and everything works. But there are options, and you can use it, and you can play with them, and it's like not a given that you would always reuse just the most probable word here. If we look at training a transformer neural model, it's still the same architecture, but we actually do something slightly different. So the idea here is that we want to, we have some data, and we want to just reproduce exactly the same text that we have in our data, and we always just predict one next word and not the whole text in one. So it's not like here we would do this autoregressive decoding that the feedback generated stuff. This is not what we do in standard transformer model training. So we basically start with some random parameters and we input some kind of an example, and whenever we don't hit the right word, we need to update the parameters. So if you imagine this kind of sentence, let's say it's from a restaurant review, and we have a language model that wants to predict the next word. If it predicts the correct word, we're fine. Nothing needs to happen. If it predicts a wrong word, that's a problem, and we need to update the parameters. What if we predict a word that is exactly, that means kind of the same as the correct word? What happens now with the transformer? If you have this it's the same word more or less, right? It's just like slightly differently phrased. So even if the transformer predicts this word, it's very close, it's not quite the same, and again it has to update the parameters. It's just not the exact same word. So this and this are kind of like the same amount of wrong for the sake of transformer training. And the same goes for cases like this. So here, you would potentially generate the correct word at a different position, at a later position in the sentence. Again, the sentence, if you read it like this, blue spice is in the expensive price range, it means exactly the same, but again, it's the same amount of wrong as saying the exact opposite of what's in the data. So the point here is that this is all like really low level, and there is like absolutely no concept of what a sentence is, what a text is, or what the purpose of the text is. So it's just something that I believe we always need to bear in mind, even with LLMs, that this is what they are pre-trained on, and this is the type of criteria, just like predict the next word. So basically, it's always just you feed the data in parallel, so all of these come in at the same time, and you try to predict all these things in parallel. And that's kind of what makes transformers work, because if you can do it in parallel, you can do it at scale, and the sheer scale wins. So that's basically the reason why we can even have such big models in the first place. The training criteria or training approach is like really really basic. Basically these things, these predictions don't influence each other. The only influence here is via the attention layers inside the model, but these predictions take place entirely in parallel. So that's training. I'm probably not gonna go into basics of training, because I'm kind of assuming that you've seen this a million times, but so like training with gradient descent and it's exactly the same as for any other neural network. There's like absolutely no difference. You have the same fiddling with optimizers and with the learning rate and stuff like that. Maybe one thing that I want to mention here is that in general in most situations you see this basically this type of graph, right? You have this like training loss going down, and then you have the test loss at some point starts to shoot up, and it means that the model is overfit, and you need to stop the training here. Here it's not so certain, and I'm still not sure what to think about this. Essentially, if the models are kind of overtrained so much, they can start to actually try to interpolate the training data, and this is something that we might be seeing in LLMs. And I'm still not sure like what to think about it or like how to interpret it. It's just something that doesn't fit the standard image of what training and like the training error and test error should look like. So that's just kind of like a remark on this. Otherwise, it's like really completely standard training as you would do with any other neural network. The kind of main advantage or main improvement that comes from all the pre-trained language models as well as LLMs is self-supervised training, which is something, for instance, that hasn't been done in machine learning until recently, because everyone had so much data that it didn't matter that much. But for a lot of like pre-trained models that are used elsewhere, this was actually quite useful. And the idea, originally comes from the BERT pre-trained model, which was essentially even from previous pre-trained models. BERT was just the first transformer, where you could basically either use some naturally occurring labels, as in if you predict just the next word, you can then use any kind of text. Or you can somehow corrupt data and learn to fix them, and this is kind of what BERT is doing, which is you just mask a word and then try to predict what word was under the mask. So here, the main point is that you can train on like huge amounts of data, because you have all the you can just download the whole internet. You have regular texts. And that way you can essentially like pre-train a language model in a self-supervised fashion before you can fine-tune it on your own task-specific data with your task-specific labels, where, let's say, for instance, you have like gigabytes of data, just text, and then you have a few thousand examples, few thousand sentences, for, let's say, language understanding in dialogue, where you have labels, where someone had to write the labels, and you can basically pre-train your language model on the general data, and then fine-tune it on the task-specific data. So you basically start with like pre-training on some kind of a huge data set, and then you can use smaller data, and you usually then can get away with using relatively smaller data for the fine-tuning. You can kind of think of these pre-trained models as like pre-trained contextual embeddings. You can think about them as like better like word-to-vec embeddings. But you can also say, okay, this is a whole model. It just depends on the view. It's exactly the same. It's just like a transformer model, and you can take the outputs of the transformer model as embeddings, or you can just use the model and assume that it's like the whole architecture that you need. And this like basically determines the model capabilities. And actually, like the larger your model, the larger the architecture, the more data you probably need. There are some scaling laws which aren't really laws, but more like ideas about like how much data you should use to train your model. You can kind of see like how different LLMs recently have been trained. But the main point anyway is like the more data, the better, essentially, and the data really influence basically everything with the language models. Now, this also means that, you know, if you just like pre-train on the whole internet, you have a lot of ready-made models, and I suppose you've probably seen the Hugging Face library, and maybe you've seen Olama, which is a nice tool for running LLMs locally. So you can basically just get a lot of these models from the internet, and they just work. You can just download and use them. Either it's you know, it's a basic pre-trained language model such as BERT or GPT-2, or I don't know, like BART or T5, and then you have, you know, you can download them, but for themselves they are not that useful, and you need to fine-tune them on your own data so that they're actually useful for you. Or you download an LLM, and in that case, typically you can just use it, and it should be like ready to, you know, be just prompted with some inputs and be somehow useful. I'm gonna talk about that point in a second. A few of you know, some of these models are just open, and you can download them, you can tweak them, you can see their parameters, you can get their prediction probabilities and stuff like that. For other models, especially the ones from OpenAI and from some other companies as well, yeah, they're basically closed, and you cannot see what the models are. You cannot even see what their architecture is, or they don't even report that. So we don't even know, how big GPT-4 is, for instance. And you can just use them using an API. You can just, you can use them, but you basically don't know what you're using, and it's a complete black box. So it's kind of, to bear in mind. And I suppose you know about the situation that these like commercial or closed models usually perform better in a lot of tasks. But then if you want to have like full control over what the model is doing, then you probably need to go for one of these open models. So just to illustrate this, there's like a huge number of models appearing essentially everywhere, and it's obviously driven by the largest tech companies, but there's like a huge choice, and there are some ways of comparing them. There is a like the LLM evaluation suits in chat where you see the models compete against themselves, and you can see what model is on top of the leaderboard. But there's like a huge choice of different models, and the distinction between like what's just a pre-trained language model, what's a large language model, is kind of on size. You can say that if the model has like over 1 billion parameters, or I don't know, over, let's say 2 billion, or you pick the boundary. There's like, it's not clear cut. You can say that this is the distinction. On the other hand, you can also define it just by the behavior. And there are still some discussions as like how do you define it. Some people want to define like all these pre-trained language models, such as BERT or T5 or these things, as LLMs. I would say they're probably not. I would define it by saying the pre-trained language models are good for fine-tuning. The LLMs are kind of useful even without it. But I know that this definition also has problems, as in some LLMs are released as like a base model, and then there's like a chat-ready model, and it's the same architecture, same type of model, with almost the same name, and you know, to consider one of them an LLM and one of them not an LLM is probably also wrong. So there is probably not a good definition or not a clear boundary anyway. So I'd say we can just enjoy that we have them and ignore the fact that this is not really well defined. But for the LLMs, the main, I would say, like a really important property is that that you can just prompt them. You don't need to fine-tune them. You just show some examples or put like a question in or some reasonable prefix in a prompt. And given the fact that these language models have seen a lot of training data, if you give them some examples, such as, you know, in here, they can see that, I don't know, this you know, these examples show the sentiment of the sentence, right? So the language model is likely to actually generate the sentiment label here. In these examples, it's exactly the same. It's just about the topic classification. So you could say that, you know, this is like the original prompting, where you prompt with a few examples, and then you decode the output. But nowadays you can obviously go much further, and you can include a whole set of instructions in the prompt. And you basically play with the prompt, and you can get a better output. This is the prompt engineering. The example based prompts are usually called few-shot prompts, because you have a few examples there. Or you can go for a zero-shot, where you just like tell the language model what to do. There's a whole area of prompts where people kind of force the language model to think step by step, which means that the language model is kind of supposed to generate intermediate outputs, and then it, you know, like, given the fact that it just doesn't just generate the output at the first go, and it goes step by step, it should improve this output, and there's like a lot of extensions to that, which I'll mention in a moment. So that's kind of, you know, the main property of LLMs is this, and you could say that if you train a language model for long enough, for long enough data, it will see something like this. There will be something in the training data like this, and eventually the language model will you know, by itself start solving these tasks just by being prompted. Or what you can do is kind of help it a little bit. So that's what most LLMs are doing, which is essentially the language model is not just you know, it's not just like pre-trained on these self-supervised things, pre-trained on just predicting next word, but it's also fine-tuned, or maybe pre-fine-tuned, whatever you want to call it, for being used with prompting. So essentially, it's just, you know, in domain data, it's exactly the same type of training. You're still just predicting the next word, but the data look like stuff that you want to feed into the language model later. You know, the kind of tasks that the language model should be solving. So you have a lot of data sets that have like a lot of different tasks, you know, where you would have the input with some assignment, potentially with some examples, and and then you have a solution here, and this is what you fine-tune the language model to do. And given the scale of the model, given the pre-training on unlabeled data, you will get, or you should get, the ability of some generalization to some tasks that the language model supposedly hasn't seen, or it's a question like how far it actually generalizes and how far these like new tasks need to be similar to what the language model has seen, but you do get some generalization. And this is also why some LLMs are released as like a not instruction tuned version, and then you have an instruction tuned version that is usually the one that is more useful in most cases. So it's basically just adding better data and keeping the training exactly the same. But there's also another step further. So we're not just doing instruction tuning. We can do some reinforcement learning, or we can do some learning from human feedback. And this is again like one of the improvements of LLMs over just base pre-trained transformer models. And with reinforcement learning, basically the idea is that we're learning from a weaker supervision. We only get some feedback once in a while, so it's not like we predict the next word at every step, and for each of the next words we get the feedback. So this is good for us for some like global optimization of the sequence generation. So you don't know if a certain step, like a certain word that you generated, is good, but you know whether the whole sequence, the whole output, the whole text is good. And we can basically frame this as a set of states and actions and rewards, and kind of the original idea, or like the idea where you illustrate reinforcement learning, is that you have a robot that moves in space, and the state kind of indicates whether the robot is like in this spot or this spot, and you can kind of imagine that your space is the space of all possible generated texts, and the state is essentially what you have generated so far. So like the prefix, and in this like robot moving, the action is like go forward, go backwards, go left. Here your action is like generate this word or some other word. The issue here is obviously how to define the reward. So the idea is that that there's your LLM or your model, and it takes some actions, which means it generates stuff, and the environment basically like changes its current state. That would be okay, but it also gives it some reward, and the rewards are a bit of an issue. And I'll show how this is solved with LLMs in a moment, but it's like generally problem that you need to have some external reward model. And training for reinforcement learning is basically trying to maximize the expected long-term reward. So you're optimizing your policy, which means you're optimizing the way you choose the next word when you generate. So that's kind of what we need now for reinforcement learning from human feedback, which is essentially just on top of the instruction tuning that you saw just now. We have some reinforcement learning improvements. And the idea basically is that you have the base language model, and you generate a lot of different, feed it a lot of different prompts. You generate a lot of different outputs, And then you have humans. So you hire some people, you need to hire a lot of people, they're probably not well paid usually, and you just have those people rate the output. So you just like have them like give a thumbs up or thumbs down, or some other thing like comparing, like this output is better than that output, or and so on. And you can use that, and obviously you could just take this and feed it, feed those people into the reinforcement learning. So you could say that, okay, this reward comes from people, right? That would work technically, but the problem is that even though you don't pay the people very well, they are still too expensive, and you still need so much data. That what is usually done is, instead of using using the human feedback directly, you train some other, usually some kind of another language model that is trained to mimic the humans, basically just to train to get a prompt, get some output, these two things, and then it will predict some kind of a score for the output. So you essentially trained this reward model, and you can now say that, okay, this comes from some kind of a reward language model, and this is your LLM that you're trying to train, and you basically use another language model to train your LLM. So the idea, you can look at it like this. You have your prompt, and you have your initial model that you started with. You have your model that you're trying to tune using reinforcement learning, and then you have some reward model that you feed into the outputs. You can check how far you are from the initial model, and do some weighting, and you can update your model based on the reinforcement learning. So that's kind of the whole idea. But the main point here is, and this is what is enabled by the reinforcement learning here, is that your reward is global. So you're actually rating the whole text, and you're checking whether the whole text is good or not. It's not like you would be checking whether you hit the right word at every place. It's global. It's over the whole text. So if you, let's say if you generate something where there's like one more word and the rest of the words are shifted, and it's exactly the text you wanted, it will still probably get a very high score, as opposed to in the initial training where you're not hitting the right word at the right place, and you're getting essentially a very low score. So this is like the main kind of qualitative improvement from all the previous stages of training. This has the disadvantage that you're using reinforcement learning, and I don't know like how many of you have tried to train something using reinforcement learning. Not many, some. I'm not sure if this is your experience, but my experience is it never converges, and it takes forever, and it's not stable, and whenever I can avoid it, I will. So that's why there is also like a reinforcement learning free alternative, where you basically have a specially designed loss function that I'm not gonna try to explain, because I'm not sure I still understand it since the time I made the slide. But the idea here is that you essentially have a loss function for that has a pairwise text preference. So you know when you have one preferred text and one dispreferred text, and you essentially like are able to directly modify the model to shift the probability distribution in favor of the preferred text. So there are some variants, even though I would say that most LLMs still use the reinforcement learning variant. So essentially, to kind of sum it up, you can start with a random neural network. Then you do some pre-training, which means that you just you just try to predict the next word at every step, and that means that what you get is something that this is what my postdocs they called autocomplete on steroids, and I very much subscribe to the idea, because this is basically what the pre-trained language model is. It can just predict the next word in a very clever way. And then you can move on a little bit, and you can do instruction tuning, where you get stuff like this, and you basically train the model to solve problems or to follow the instructions that the model is given. And what you end up with is some kind of an instruction tune model that you can say is potentially will attempt to assist you. And what you do as the final step is this human preference optimization. So either reinforcement learning or some kind of other training technique where you optimize globally. And hopefully you will end up with a language model that is a helpful assistant. I mean, this last step, you may have heard the term alignment, which is basically, it's supposedly aligns with human preferences, and therefore it's more helpful. But this is essentially how you get like a full LLM from scratch. In these steps where you burn I don't know how many megawatt hours of electricity, but in the end you get an LLM. So that's kind of as to the training. Now you probably heard the term hallucination, and you might have seen hallucination as well. I would just want to show a few examples, and I'm not sure if this, is it working? Someone tried to convince ChatGPT that 2 + 2 = 5, and ChatGPT apparently, it wasn't convinced at first, but after a few attempts. They actually got ChatGPT to output stuff like this. So if you try hard, you can convince the language models of that. The other issue is if you ask in a specific way. I'm actually not exactly sure what plant this is or how it looks like, but it's apparently highly poisonous. So if you ask for recipes with that, you can get some nice suggestions for poisonous tea from an LLM. The thing is, basically the LLMs are kind of like eager to please. They always reply. They can be swayed, and what you get is often incorrect. Now the problem is why, and I'd say if you look at the training steps, do you notice something that's kind of a problem with the type of training that we've been doing for the LLMs? Is there, for instance, like, what do you think it's missing in the training, or what do you think it's kind of needs to, would need to happen for the language model to actually not exhibit this behavior. Yeah?
Well, first of all, it could be trained to be less pedantic and more self-reliant, so it trusts more answers more. But what the real problem is that it has no internal representation of what it is saying. It only is using statistics to predict the next most likely token. It doesn't know what it's saying. It needs to actually have some kind of knowledge. It needs to actually know what it's saying.
I would say that's basically that it has like no representation of what it's saying, just predicting likely tokens. Yeah.
Does it have any way of actually keeping disproving the user rather than like actually just agreeing with the user no matter what?
Yeah, that's the other thing, that it basically tends to always agree with the user, and I think that like some recent language models might be a little bit more confident, let's say, but yeah, it mostly just goes with what the users say and never doubts anything that the user feed it into it.
Yeah, I think this is a case of where it strives to vert from the reference policy towards the policy that has been chosen by the humans while doing instruction tuning with reinforcement learning, because it like appeases the user's stripes.
Yeah.
So far, and the hallucinations are, I think, kind of inevitable because you are just predicting next tokens. But if like instruction tuning manages to make it say that, that there is no such thing as a drop of belladonna, that might solve this.
Yeah, you're right that if you feed in stuff like I don't know, essentially, or there is no such thing, or some disagreement with the user, and if you feed it into the training data, you might be able to solve at least part of this. And that's actually like one of the biggest problem here, that there's like none of the training steps that I've shown kind of cares about whether what you reply is correct, because even with the human preference tuning, it's like it's not about what is correct or what is wrong. It's about what basically looks best to the people that check those outputs, that just give it a thumbs up or thumbs down, and is purely based on whether they like the output or not. It's not about they're not paid so well that they would do any fact checking or anything like that. It's just this looks good, this looks bad. That's it. So it's kind of like that the language models are kind of bound to hallucinate, especially in the current setting. What I heard from, we had a talk by Anna Rogers like 6 weeks ago in our department in Prague, and she actually pointed to this term that language models are bullshitting, because it's not like they would, they intentionally mislead. It's not like they are, when they're hallucinating, that they are somehow experiencing a malfunction or something. When you are hallucinating as a person, it's there's probably something wrong with you. You're either, I don't know, under the influence of a drug, or you're ill, or there's something wrong. With language models, there's nothing wrong when they're hallucinating. It's like the normal mode of operation, and that's why I think it's kind of fitting that you could call this bullshitting, because and she referred to this paper that essentially says, okay, the problem isn't that they hallucinate or they lie or something like that. They're basically just not designed to represent the world or represent the truth. They're just designed to be convincing, just to produce convincing text. So that's this is something that we probably need to bear in mind at all times. But still, we can try to mitigate this somehow, and you can still make use of language models quite a lot. So it's just as a warning here.
Ondřej, I think that even the use of the word hallucinate sort of is indicative, right? Because hallucination is a perceptual phenomenon. And it's like saying
Right.
the language model is perceiving something, which is already anthropomizing them, right? It's
Yeah,
not true.
yeah,
They
yeah.
perceive nothing, they just produce stuff.
Yeah, but
So
yeah,
if you wanted to call it a lie or a fabrication, that would be fine because then it's a production-related thing. Right? So
yeah,
already we are-
that's actually a good point that I didn't even realize. But you're right. Hallucinating means like perceiving stuff that isn't real,
there.
right? Whereas,
I don't know if these things perceive anything. I don't think they perceive
Yeah,
anything. They just
yeah.
produce.
yeah,
And
yeah,
so therefore,
yeah.
if you call it like fabrication or confabulation, that would be fine.
Mm.
But I think this is closer. Namely, they were never designed to represent the word anyway.
Yeah, yeah. I suppose the problem is that someone, I don't know when, like several years back, called it hallucination, and since then everyone has been using that term. And
Exactly. I don't. It's too late to fight that battle.
yeah, yeah,
But hallucinations are like creations of our brain, I would say.
Yes, but think of hallucination. It's a perceptual phenomenon. When you lie to somebody, you're not hallucinating. You're lying.
I mean, you could technically say that, you describe what you're perceiving just now, and when you hallucinate, what you describe and what you say, it doesn't make sense or is not true. But I suppose, yeah, a hallucination, it means that you just saw it or you felt it.
Isn't it like you are perceiving the reality in a different way than the reality?
You're assuming that the model perceives anything else.
Or that you are creating like a new reality which
So
doesn't
again, you're assuming that the model has a notion of reality.
Yeah, but the thing is that the model, we can't say anything about how the model perceives or,
Yeah, I mean,
Or even that it perceives.
yeah.
yeah, I mean, my question or my point is, I don't know if hallucination, I mean, we need to perceive to hallucinate. Or maybe it could be like with for example, we are sleeping, we have our eyes closed, we hear absolutely nothing, and we could still like have some kind of hallucinations because we are creating something.
I think Finn has a hand up. Let him say something.
I
If we
think,
can
I think the term hallucination actually was first coined when they were talking about it when Transformers were still relegated to translation, or when they were first talking about machine translation, because they would spit out words that were not actually in the initial target language, source language. So like it would be trying to translate a sentence and then it would add something new that wasn't even there. That's my idea, but I don't know if that's...
Yeah, I suppose this is where the term comes from, but I don't think this, that it's any better than the current use. I think it's still the same problem that
Yeah.
there is some assumption that the model somehow has a perception or, yeah.
Maybe you can understand the word hallucination more in a way, instead of seeing something that's not there, that would be about perceiving something, but more understanding it in a way that making something up that's not there.
Yeah.
So that would be about producing something instead of...
It could be fabricating.
Yeah, but yeah, that would be fabrication, or like the fabrication would probably be like a more accurate term for that.
Can argue about
Yeah,
it.
yeah.
What I'm saying is that we tend to assign so many attributes to these models that don't exist, including the fact that they perceive or that they have a model of reality.
I mean, to me, this, like even like even the term attention
Yeah.
itself is kind of anthropomorphizing the models, and I never realized it until I read, basically one of my colleagues was writing some kind of an article in Czech, and I read it, and he actually translated attention into like the Czech word for attention, and it felt so wrong, like straight away. I guess this is just like, when I live in the English terms, they're kind of, I don't feel them as much probably because it's not my first language, but
I feel like that's a problem with like any new field when you're coming up with words to describe something.
yeah, I suppose.
You need a lot of ambiguity and confusion when you already have a word and you're just reusing that word for something that it's actually describing something new.
Yeah, that's right. Yeah, and maybe I'm just like so used to the English term that I don't even like bat an eye, and I don't feel like I'm anthropomorphizing the model when I'm using it. But when I suddenly hear it like completely new in Czech, yeah, it's like I would be like coining the new term, and I probably wouldn't do that. So yeah, you're completely right. anyway, so we still have this problem, and I'll just show like a few things that you might want to do to improve this or to just like improve performance in general. So the one thing is a while ago I mentioned chain of thought or chain of thought prompting, which is basically just we're just telling in the prompt we're just telling the language model to like think step by step. You can actually take that much further. You can. And this is what the so-called reasoning models, which is another anthropomorphization, are doing right now. So basically, the idea is just that you try to make these chains of thought very long and train the models to produce this. So the models are not just prompted to produce chains of thought; they're trained to do this. So this is what I don't know, like DeepSeek or the OpenAI 01 and 03 and these models are doing. And you can train them with, and there's again a reward model that is rewarding them for like the partial steps in the chain of thought. And it turns out that the longer you compute and the longer your chain of thought is, the better results in general. And there's like more research into this, looking into not just like going in a linear chain, but looking into tree search, where you can go over some intermediate steps and then backtrack and do this kind of stuff. Even though apparently just like linear chains still seem to work well enough. So, but there's quite a lot of research into that. And there's also some research into budget forcing, where you can, for instance, you can just like force the code weight in the model, and then the models should start trying to find some alternative solutions, because obviously when you say weight, then the next likely tokens would be weight. This might not be correct. I haven't considered X and Y, and so on. So you basically like artificially prolong the chain of thought using this, and you can also try to like force terminate the thinking. So you can basically try to make the chain of thought into like a specific length. So that's kind of a way of doing this. There's a lot of reinforcement learning when you have this process reward models, and you can again train the models with reinforcement learning, and that's actually like what DeepSeek has done. And there's like a specific reinforcement learning algorithm where you just produce a lot of outputs, and then you basically look at which ones of them are better than the average, and then you upvote those. So that's like one way of improving the models. And the other thing is you can actually essentially like carry over the idea that we produce some outputs and we rate them, and we use that as feedback for training, and you can just take it earlier and use that even in the pre-training phase. So you can take a lot of data generated by some base version of the model, and then rate that data somehow, and just take the good parts of the data using some rating model, and then you can use this early in the training. You can use that for pre-training. And this is useful, for instance, if you want to do this, training for the chain of thought. You probably need to have some labels or some feedback into, that these steps are good, and these steps are where the model has made a mistake. So So there's one place where you want to use a lot of synthetic data. You also might want to use cleaner data with less noise or more data than you would have available, or in general, you can play with the data, as in like you can rewrite some data as problem solution pairs using the base model and then use it for instruction tuning, or you can if you have models that are multimodal, then you can synthesize audio data to train your model from some text data. So this all can improve the models. Obviously, it's only up to a point, and you're not like removing the basic problem that you're having. And you always need to filter the data so that only the best generated outputs get actually used in the model. This is you can either have like the model evaluate itself, or you have an external model, or you can also, what you can do is, and this is part of what I'm just gonna say in a second. If you have models that generate some programming code, you can actually just like run the code and see if it works or not. So there, the validation kind of solves itself, and that's basically like the last thing that I want to mention here, like of the things that you can do to improve the LLM outputs. And this is also what most current, especially like the commercial LLMs, are already doing, which is so-called tool use, or the idea that basically as the model is generating stuff, it can retrieve some additional information, or it can basically delegate some tasks to some external tool. And this could be, just that, for instance, the model can generate a bunch of code and then run it and then give you the result. Which like if the task is kind of well suited to that, we tried it with this is GPT-4o, and it just produced this output that makes perfect sense. Or it can have like a set of API calls that it can use, and this was actually like where this originates from. This is the tool former model, which had like five different tools that it could use, some calculator and question answering machine and stuff like that it was able to then use based on the user inputs. So the LLMs are basically just tuned to do this right now. Again, part of it will be using synthetic data, and all these things kind of move into like better accuracy and better capabilities, but obviously you're still like relying on this inherently kind of disconnected model that doesn't have like a direct connection to the reality. So yeah, so this is basically what I wanted to say about LLMs in general, and I'm not sure if we want to take a quick break now or slightly later, because the other bit is a little longer. I'm not sure. That's kind of up to you. Break now or in like let's say 15 minutes or something like that.
What's that? I could wait 15 minutes.
Okay. So let's go to the other part, which is basically I'm going to be looking at dialogue and dialogue systems and in that, there's one step which is response generation. I'm going to be talking a bit more about text generation in general there, because it's kind of like the part of dialogue systems that interests me the most. And I'll try to like include the usages of different transformer models in there, but I'm gonna also mention stuff that was like, you know, used prior to that, or some like rule-based approaches and things like that. So this will be like more of like a general NLP stuff. Right. So I'll start with essentially like a definition of what I mean by a dialogue system. And that is like any kind of computer system, and I mean usually I would say it's just like the main point in this, or the main part of it is software, which is designed to interact with people in natural language. And this is kind of intentionally left quite wide, and it covers quite a few different cases. And that also means that there are like different subtypes of systems, and what I want to focus on, or like the distinction that I want to focus on, is mostly between task-oriented and non-task-oriented. And I'm going to look at task-oriented most of the time, because they are a bit more structured, a bit more complex. There are a few more NLP tasks to be solved there. So the idea for task-oriented systems is that they're just like, the main point of talking to them is that you want to solve a problem, that you want to accomplish a certain task. You want to book a restaurant or book a flight. You want to find a bus schedule. You want to set up your thermostat or stuff like that. And this is, in my view, like this is like the most, or I'm not sure if you can, but historically this would be like the most actual dialogue systems, or most purpose-built dialogue systems that you can encounter. And typically these systems would be built for like either single domain or just or multi-domain, which means that you have like either one topic of conversation, and you have a system that can only talk about, let's say restaurants. It's like one of the examples that have been used in research quite a lot. Or you can have like a few topics, so it can do like restaurants and hotels and taxi and buses, let's say. But other than that, you know, anything you say, the model would just tell you that it didn't understand you. So that's kind of the idea of like a single or multi-domain system. In the non-task-oriented setting, that historically would be mostly for just some social conversation, and you basically like the point of the conversation is just the conversation itself. You just want to be entertained. You want to talk to someone or something. These systems would often be designed to project a certain personality, and there were also, competitions and occasions where people would be trying to pass the Turing test, basically convince someone that the system is human or intelligent, even though it's purely on behavior. So it's more about trying to like game the test, or trying to set up the people or fool them into believing that the system is human. And these like non-task-oriented systems are typically designed to be open domain, which means that they talk about basically anything. Now, if you want, if you talk about like real life applications or existing dialogue systems, I suppose, if you've chatted to an LLM, which like who hasn't chatted to an LLM here? Then you have used like a real life dialogue system. And I suppose you probably have most of you probably used like one of these API only closed models that you can talk to online. Maybe some of you downloaded a model and ran it locally, but in any case, it's just, you know, it's kind of open domain. I would say you can argue whether it's task oriented or not. I would say maybe both, but it's like, you know, the tasks historically in dialogue systems are like much better structured. It's like you really know what exactly you need to do to, let's say, find a bus schedule. There must be like a bus line and a departure place and departure time and the destination place. You know, with the tasks in ChatGPT and so on, it's by far not as well defined. And obviously, you always need to deal with hallucinations. So this is I'm not sure what ChatGPT would do now. This is like GPT 3.5. So basically, like a year and a half ago, I asked ChatGPT who I am, and I got like a very plausible text with you know, small issues. I mean, I guess it was a slightly more flattering than what I really am, but you know. You always need to, and this was what Ondřej was asking about, like when you can believe LLM outputs. I'm not sure, to be honest. I don't know what I would reply to him when he asked. So basically, you can ask about anything, you can feed anything into these systems, and you get some reply. Now, another kind of, I would say, prominent example of like real life dialogue systems are these various virtual assistants. And now that would be interesting to me, like who is using a smart speaker or has used a smart speaker or similar device? Okay, so just a few of you. So there's actually like much less than I would expect that in like this kind of population it would be slightly more, but okay, so these are, because I've read some like market penetration reports and stuff like that, and at some point there was like a smart speaker in like a third of American households, and I mean similar rates across Europe, definitely much less here in Czechia, because like none of these systems built by the large companies was actually able to speak Czech, so it's definitely a barrier. But anyway, so you have these devices. You have either smart speakers, or the other option is, I mean, if you're using an Android or an Apple phone, you have a virtual assistant running in there. So you have Google Assistant, you have Apple Siri, and these things are like fundamentally different from the LLMs. And this is like closer to the like historically defined dialogue systems. So these would be task-oriented and multi-domain systems. So these are basically, you can control your music, you can get news, you can get weather, you can do a lot of tasks with them. You can control your smart home, but all of these domains, all of these functions are programmed in by hand. So basically, Amazon and Google and Apple all had large teams of people that programmed all these functions in. And technically, you were able to add your own with a lot of limitations, though. And these systems, essentially, if you had any of these devices at home, you probably know that there was a lot of concern about like when these devices are recording the audio and sending it off to Amazon or Google. The issue is that basically these systems only listen to the so-called wake words. So you just say, "Okay, Google," or Alexa, or "Hey Siri," or stuff like that. And after you say it, basically everything, the whole audio, everything is sent to the vendor's servers, and everything is basically working online. So basically these things are just a set of relatively good, reasonably good microphones, and not a very good computer. that is only able to just like check for when the user says the wake word and then just start sending the audio to the server. But in any case, these are like, again, like I would say like the first very large deployment of dialogue systems that, you know, a lot of people have seen or work with, and now the LLMs are kind of like the second generation of that. The dialogue with those systems here was kind of limited, though. I know that with ChatGPT you can kind of, you know, talk to no end, or like the dialogues can be pretty long. With these systems, it's usually you just ask them to do something or to tell you something, they respond, and the dialogue ends. So it's just like, you know, one question, one answer. In most cases, obviously, you can ask follow-up questions, or you can, like, the dialogue can be longer, but you know, it's more of an exception than a rule. So these are kind of two real-life examples of dialogue systems. And now, this is an example of what I usually will have in mind when I talk about training systems on some data and accomplishing dialogue tasks. This is an example of a research data set called MultiWOS, which is basically, I would say, yeah, the benchmark that everyone has been using for the past like 6 or 7 years. And it's a multi-domain data set that has, you know, just a few domains, so it kind of acts as a travel assistant for people coming to Cambridge, which is where it was built. And you can ask for, I don't know, like a taxi to your hotel, or you can ask to book you a restaurant. Obviously, it's like all kind of made up, even though the restaurants and hotels do exist, but the whole dialogues are kind of staged. They have been collected by people on crowdsourcing over the internet, and you have 10,000s of dialogues and a lot of annotation. So like this was like a massive task to accomplish, to build this kind of a data set. That's why there's basically like only one such data set. I mean, there are data sets of similar size, but they usually have some kind of a caveat, like they're partially synthetic or things like that. This is actual like conversations between two real humans, obviously staged, so they're just like acting out their roles, but still it's like a human playing a tourist coming into Cambridge, and another human playing a tourist assistant that has available a database to search for hotels and taxis and trains and things like that. So you can see that, you know, there's a lot of annotation here. It's like checking the user preferences over time and the database results and everything, and you have it available, and you can use it to train your dialogue system. So that's kind of examples for the task, and you can kind of see that, you know, this is slightly different from either of these. Here you have like much less structure. It's much wider, and you know, it's a bit less. You're a bit less in control. Here it's like much less complex dialogues, but you have more domains. So you have more different functions, but the dialogues are kind of shorter. Now, if we look at like the traditional architecture of a dialogue system, or how you would build a dialogue system, and you can kind of say that, you know, like these systems are essentially more or less following that architecture. Again, we don't really know for sure, or we just know some hints because the architectures aren't public, but they are basically like compliant to this architecture. So the traditional architecture looks like a pipeline, and it's just like several tasks or modules accomplishing different tasks connected. And if we imagine that, you know, that this is a voice-based or spoken dialogue system, you start with speech recognition. So basically, the user says something that is then transcribed into text, and then the next step is the language understanding or natural language understanding module that turns the text into some kind of a structured representation that is then used internally by the system by the dialogue management step. The dialogue management is trying to keep track of the dialogue state, which means mostly about keeping track of the user preferences that stay expressed over the time of the dialogue. So, for instance, here they're kind of checking what type of restaurant they would like, what price range, and what area, and then there's the dialogue policy, which basically decides what to do next. So the dialogue policy is just looking at the current dialogue state and trying to decide what action to take. And it also has access to a database or to some kind of a backend API where it can check, for instance, in this case, there are too many results for restaurants that would be Chinese and cheap. So the good idea would not be to just put in one at random, but if you have a lot of them, we can perhaps ask which area the user would prefer. So that's the idea here. And then once we have this action, it will again be in some kind of a formal representation. And what we need to do is to generate the response, to basically convert this into some kind of a sentence that the human would understand. So that's the natural language generation step or response generation step. And if we have like a voice-based or a spoken system, this sentence is just read back by the speech synthesis. So this is the traditional pipeline where you start from voice, go to text, then to some kind of a meaning representation, and on the meaning level you get the reaction or response, and then turn it back into text and voice. Obviously, if I don't know what this is doing. Sorry, I'm really not sure what this was. But I'll try to just reopen it. Okay. So obviously, if you work with a text-based system, as would often be the case, just if you're just working on a website, these two systems, speech recognition and language speech recognition and speech synthesis, I basically just cut out of the loop, and you can have a shorter loop, and it still works text-based. Basically, for anything better than basic chit-chat in this architecture, you would need some kind of a database backend, and this is also kind of true for LLMs, even though they have a lot of accumulated information in their training parameters. So for them, you get a lot of responses beyond chit-chat without any kind of a backend. But still, if you do have the backend, if you have this tool use capability, you can get much better results. Right. So that's the traditional architecture, and I guess I would probably make the pause here, so that we can then go into the individual steps one by one and look into how we would implement them. And I would, by the way, I'm intentionally skipping speech recognition and speech synthesis, because I'm kind of guessing that they're You probably would. It would be better if you teach me about those than you listen to me telling you something about that.
No, it's more than that. They already had lectures in speech recognition, and there's going to be half a day on synthesis.
Oh, there will be. Yeah, I saw there was something on recognition, so I thought, okay, but I wasn't sure about synthesis. So that's next week.
Yeah, there's a team working on synthesis.
Oh, okay. So that, yeah. So I'll just stay in the text domain. Okay, so I don't know.
Let's take a break. It's 3:10 now, so we start at 3:25. 15 minutes?
Okay, let's continue. So basically we just saw just a few examples of some dialogue systems or dialogue system tasks, and we've seen the traditional or the standard dialogue system architecture pipeline. And now I'm going to basically go one by one to these 4 steps of the text-based pipeline, and I'm going to show some issues with those, what the tasks are, what the potential implementations are, and how could we potentially use LLMs for some of them. Right. So we'll start with the natural language understanding, or sometimes you can see natural language understanding or spoken language understanding. I'm gonna just use language understanding. It's kind of all the same for the purpose of this talk. Otherwise, you can potentially distinguish between spoken and text-based systems. But the main point here is that we want to extract the meaning from the user utterance, from the user input. So basically, we can get sentences like this. We can hear something like just someone saying, "Oh, Chinese city center," or they could say something like, "Oh, I've been wondering if you could find me a restaurant that has Chinese food and it's close to the city center, please." And you can see that for the purpose of a dialogue system, like this one where it just looks for restaurants or hotels or things like that. These 2 sentences that look very different have kind of exactly the same meaning. The user basically wants some Chinese food, and they want them close to the city center. As the only information that we are kind of interested in, and that's why the kind of standard semantic representation that is used in language understanding and in these limited domains is also kind of limited or kind of shallow. So the standard representation you would use is usually so-called dialogue acts, and here we have the intent or potentially intents or act types, which are like the general meanings of the sentence. So in this case, the user is the user is informing about something. So the user is telling us something. By the way, these are kind of like the set of these intents. I mean, here I'm using kind of like just general functions of the sentences in the dialogue. The user is either informing about something or requesting or confirming or stuff like that. This is like not a given, and you can design your own functions, and they might be like much more fine-grained or whatever. It really depends on the implementation. So this set is like never not given. This is kind of a convention that a lot of dialogue systems use a set like this, but it's definitely not a given. For instance, in these smart speakers or virtual assistants, the set of intents that's used usually corresponds to the services that people are using. So each of these services would have their own set of intents. So that the intent is like the general meaning of the sentence, like some overall stuff that cannot be like tied to certain words or phrases. But then, in addition to that, you have some kind of basically attributes or parameters, where the usual name for this is slots. So, or sometimes you can call them entities as well. So in this case, we have 2 slots in this example utterance, or in both of them, where one of the slots is the type of food that the person wants, and the other slot is the price range. And here, these slots can have either like a predefined set of values. For instance, you can split up the price range into like cheap and moderate and expensive. Or in some cases, this could be like open sets. For instance, if the slot has to do with time, you can basically represent any kind of time expression within the slot. So these are basically the main building blocks. So these are the intents and the slots and their values. You can also see in this example, when the user would say something like, "What is the address of this restaurant?" Then you can see that the value is not given; it's actually undefined, and the user is actually asking about it. So you wouldn't always have slot values. You sometimes might not even have slots. If this is also like a valid dialogue act where you only have the intent when the user is saying hello. It doesn't have any slots or values to go with. In any case, basically this means that a lot of NLU or a lot of language understanding approaches have to do with detecting the intent or finding out the intent and tagging, basically like tagging the slot values in the text, like just basically what I did right now. There are also some other more complex representations. You can represent this stuff using some kind of syntax trees or semantic trees or some predicate logic. But for most implementations of dialogue systems, historically you would just use this kind of representation because it mostly allows you to deal with the task completion without too much complexity. As to like how we would implement the language understanding, you can actually get really far with just detecting keywords or regular expressions or stuff like that. So basically, you can build a rule-based language understanding for if you have a limited domain. It works pretty well. Assuming that your speech recognition gives you good results and you don't need to compensate for that, you can definitely go very far with just keyword or regular expressions. It's actually something that happened to us when during my PhD, we were building a dialogue system for public transport around Czechia. And we built a rule-based language understanding with a lot of keyword detection and this kind of stuff. And it worked reasonably well. And after a while, we collected a lot of data and we tried to train some kind of statistical model. And it never was better than the rules, or basically it kind of matched the performance of the rules, and we couldn't get any better. Even though we had, I don't know, like let's say something like 1,500 examples of user utterances annotated by some person that knew what they were doing. So you can really get very far with keywords and regular expressions. Sometimes you need a lot of data to actually overcome this power. And if you don't have the data, which is a common case, it might be easier to just stick with rules. Even though once your domain gets larger, then it's kind of hard to expand, and then it might just get too complicated. So if you do want to get into statistical approaches, what you usually would do is for intent classification, you can just use either some kind of a transformer model or pre-trained language model, and then just do sentence classification over. There's usually this, for instance, in the BERT model, there's the first token of the sentence is called CLS for classification, and you can actually put a classification layer on top of that and find the sentence intent. For the slot values, you can either cast it also as a classification. You can basically do a classifier for each different slot value, essentially just checking, okay, is this value present, yes or no? So basically a bunch of binary classifiers trained on the data. In some cases, for this, you probably will need to do delexicalization, which is essentially named entity recognition and replacing with placeholders. So it's something that you can do by a simple dictionary. You can just replace any kind of slot values that you have, such as addresses, or if you have like a set of values for a slot. And it can be a dictionary. For instance, even if here this slot would be called something like departure time, you can replace just like this is a time expression, and the classifier should deal with the rest. So for this kind of approach, you do need delexicalization. The other option to slot value detection is slot tagging, which essentially means that you just classify every token in the sentence, and you have this BIO or IOB, whatever you want, scheme, and that basically says, okay, this is the beginning of the slot departure, for instance. This is the beginning of a slot arrival. And this is inside the slot. This is like for multi-word expressions or multi-word slot values. So you tag the first word with a B, and the remaining words are tagged with an I. This means that you can get like I know that it's like not it's not exactly visible here that you would need it, but for instance if you just say like I don't know, Boston, New York, or maybe it's kind of hard to show on this domain, but sometimes you might want to have like two different values from two different values of the same slot next to each other, and you want to know that if it's like New York, if these are two separate values of the slot, which might happen. I don't know if you're looking for, let's say, Latin American food as opposed to Chinese food, and Indian food, or Chinese and American food as opposed to Chinese American food. You want to know where the slot starts and where it continues. So you can have like multi-word values, and you can have adjacent values of the same slot. So that's why we have these set of labels instead of just labeling. Instead of just using just like okay, departure, arrival, and date. So that's why we use like the beginning and inside. But
one example would be if I wanted to say JFK, LaGuardia, or Westchester, because there are 3 airports in New York. And
right.
So JFK, LaGuardia, those are 2 different, but they're both.
Yeah, and these could be both your like your arrival airports. Yeah.
So you would need to know that the second one isn't a continuation of the first.
Yeah.
It's on the same time.
Yeah, exactly. Yeah, thanks for the example. So that's kind of the basic approach, and I just want to show basically how you would do this with like a pre-trained transformer model. This is just one approach that I would say like works well enough, and I would say if you have enough data, this would get you like probably like state-of-the-art results. So the idea is that you just take BERT or some kind of a pre-trained model, and as I said, there's this classifier token, and you can use that to classify your intent, and then you use exactly this BIO coding to tag the tokens. So basically, for each for all the other tokens, you can do the classification. The only issue here is that you have subwords for a BERT, so you always need to only you kind of ignore classifications in the middle of the word, because you don't want your slot value to end in the middle of the word. But that's like not a huge issue. You can just do the classification basically, as usual, just use BERT or some pre-trained language model as your input features, and you just have like a simple classification layer, on top. Basically, just use softmax on top, and that's essentially all there is to it. So you can just like leverage the capabilities of the pre-trained model, and you can like just fine-tune the model for both of the tasks at once, because they are essentially the same. This is kind of the same task. It's just you have the intent labels for the first token, and you have slot labels for or slot tags for the rest of the tokens. So other than that, it's relatively straightforward. There's also an extension. There's a model called the TOD BERT, like task-oriented dialogue BERT, which essentially just takes BERT and fine-tunes it on a lot of available dialogue data sets. So if you then apply this .BERT to your task, it supposedly should work better because it has seen much more dialogue specific data. So that's just like pre-trained model fine-tuning, and it's pretty straightforward. You can also do something that is like slightly, tries to be slightly more general. You can either prompt an LLM to do it, or you can fine-tune a pre-trained language model to do it. And it's kind of like a question answering style. So instead of just having a set of tags and tagging for your specific domain, you can either fine-tune a pre-trained language model or prompt a large language model to basically ask questions. And you can just like ask a simple question, and this is a question essentially, what is the value of this slot? Kind of. If you have like a short description of a slot, you can fine-tune the pre-trained language model to give you an answer to the slot, and it can actually, it can either like generate a reply, which is what you probably would use with an LLM. You just prompt it to generate, or you could even fine-tune a pre-trained language model to generate the replies. But you can also fine-tune a pre-trained language model to just basically copy out the reply. It's called span tagging, and it's essentially you just put two softmax distributions on top of the tokens. So you kind of know which basically the model is tasked with classifying which is the most likely starting token of this slot value and which is the most likely ending token. So you have like two softmax distributions, one for the start, one for the end, and you just copy whatever is in between. So that's kind of related options. With LLMs, you can basically do this without data even on an open domain. You can somehow play with what questions you ask, and like this example is trying to ask like a sequence of questions, and then it gives you like a compound intent label that is supposedly open domain. But it really depends on your task. Really depends on what kind of dialogue systems you're building. In general, I believe that this is applicable more or less to any domain. So that's natural language understanding. So we kind of fix this or try to implement this. Now let's look at dialogue management and first the state tracking part. So in dialogue management, we basically get the NLU input, so the language understanding input, and we have the dialogue so far, so we know the dialogue history, and we need to decide on what the next action will be. So we need to keep track of what has been said in the past. We need to figure out which bits of the dialogue are important. We probably want to keep track of the user somehow, and we want to interact with the backend database. And this dialogue so far, or what happened in the dialogue, is typically called dialogue history, and we model it or try to like summarize it using dialogue state, which is managed by the dialogue state tracker. So that's like the first part of the of the dialogue management. And the other second part is the dialogue policy, which uses the dialogue state to decide on what the next action will be. And if you look at the dialogue state tracking, basically the dialogue state is just like a summary of the dialogue history. It's basically whatever information the user has provided and what potentially even what they requested and what the system has provided, so that like the system doesn't repeat itself or even like recommends a different restaurant every time the user asks for the same one or stuff like that. So we have basically anything that might be needed for producing a reasonable reply. And here we can kind of implement it in some kind of a handcrafted way. We can just like say, okay, we can just take the outputs of the language understanding, and whenever we find a slot value and it's different than the previous one, we just like replace it. So we can just say, okay, the user mentioned that they want expensive instead of cheap, and we can just like replace it like this. That can work pretty well. Especially if you have a text-based system, it's probably fine. If you have a speech-based system, you probably want to deal with it in a slightly more sophisticated way and take it probabilistically. So instead of just like replacing stuff and having just like a one value here, what you would do is keep a probability estimate. Essentially, for each slot, you would have a probability distribution of what happened. This is a bit more robust. This is able to accumulate the probability over time. So, for instance, if you want, I don't know, if you want some kind of food or some specific location or stuff like that, and the speech recognizer is noisy or like the audio input is noisy and the speech recognizer is struggling, combining the probability from you saying it several times might work. Instead of just like having like a noise or just like a null value all the time, you can get with certain value up from, like, let's say you start very low and then over time you get more probability and overpower the previous value. So that way you can get reasonable performance or like usable system even in a very very noisy environment. So I'm gonna look a little into like how you could do this using some like basic approaches, and then we're gonna look again like how we can use it, how we can implement this with transformers. So the kind of like a most basic belief state tracker, so the probabilistic version is essentially just taking all our probability estimates coming from the language understanding. So the language understanding should give us some probability estimates, and usually, like with most classifiers, you would get some scores from there. And you can just look at any like non-null value of a slot. So this you would do this for any kind of slot value. So we can say that we have the food slot and the value Chinese, and we always know that we have a previous probability that was there somehow. So let's say that we could take this as the previous probability. So we have the probability of 0.7, and then from the NLU, what we could get is something like there's Chinese with some probability, let's say 0.5, and there's the null probability of like not the slot is not mentioned, so that this kind of hashing emoji probability, and we can basically say, okay, it was previously 0.7. We can multiply these two, we can get something like 0.35, and now we also have this new probability that is 0.5, and we can just sum them up, and what we get is 0.85. So this way we can just compute the probabilities. As you see, it's like pretty straightforward. So it's like we assume two options. You know, the user didn't mention that slot, so we just carry over whatever happened from the previous turn, or the user did mention the slot, and we just like add the new probability. So it's relatively straightforward. And for the null value, we just we only consider the idea that user never mentioned the slot, so this will always kind of diminish in probability. So this is basically like very rule based, but if the language understanding is good enough, it works reasonably well. The other option is that we always do basically something like language understanding or use the same methods essentially over the whole dialogue. So we always take the whole dialogue history and do some language understanding. We might not even do, we might not even need a separate language understanding module or implementation. We can just get by with this, with the state tracking. It might give us some better results, but it might be a bit slower because it takes time to process. So there's always a trade-off, because we also don't want to take too much time to respond in a dialogue system. It's a bit kind of jarring for people to wait a couple of seconds before the system starts responding. So, but this approach is what you can do, for instance, with again a pre-trained language model such as BERT, where you could do this idea that I mentioned here, essentially that you would like fine-tune BERT for picking out slot values one by one. This way you can essentially pick them out from the whole dialogue. Essentially, you can for each slot. Essentially, you have a classifier that will tell you, okay, the value is null, or the value is some kind of special value saying, okay, I don't care about, let's say, I don't care about the price of the restaurant, for instance. So that's also like a valid value that is kind of hard to find in the in the individual words or individual tokens. So. But for if it's a specific value, we can again try to find the value by finding a distribution for the start and for the end position. And you can kind of see here, this is like a movie domain, or the example is for a movie domain, and you can see that these distributions, if you look at them, they will pick out these two positions, and you can copy out the movie name from there. So you can either you can do this over the whole dialogue, or what this implementation has done is kind of a rule-based update saying, okay, we just take the previous system utterance and the current user utterance, and if we don't find the slot value there, we just use the previous one. So it's kind of not so sophisticated, and it's almost like just doing natural language understanding and some rule-based updates. But this is called state tracking in the literature. This is also kind of a issue with what people call their systems. So this has been called a state tracker, and if you look at this system and if you compare it to this language understanding system, you can kind of see that they're very similar. They're doing similar things, but it's probably just the aim of the system is mostly what decides on the name. So that's one option that you can do. The other is, again, you can just generate the reply. And you can again fine-tune a pre-trained language model, and this is again like an example where people fine-tune the T5 model, which is an encoder-decoder, where they would just feed the dialogue history there, feed the domain and the slot and potentially description of the slot, and they've just passed it through T5, and it would generate on the output the actual value. And yeah, it works reasonably well if you fine-tune it. If you want to use an LLM, there's a relatively nice idea of basically representing your whole dialog state as SQL. So you can basically design your dialog schema using SQL. Say, okay, we have these tables and they have these columns, which are the slots essentially. And then our user preferences are basically like an SQL select command. So that's kind of the idea here, and you can basically let the LLM generate SQL, because LLMs have seen some SQL, so they are kind of pre-trained to do this, and it works reasonably well. So this is again like for LLMs. Technically, you can just like prompt them, okay, here's a dialog, you can pick out the values, and it works also reasonably well. And I'll also show an example where we did that, but with like phrasing this as SQL, or you can phrase it as like even just like generating Python code or stuff like that. It probably works slightly better. So yeah, so that's essentially state tracking, or like some kind of a implementation of the state tracking step. And now we're moving to dialog policy, where it's basically us trying to decide what's next, and what do we do essentially. How do we get to a goal, which is like the final turn where we book the flight, or where we provide the user with all the information they wanted. And we can do some actions which are mostly just replying, but we can also do stuff like actually booking something, or basically operating some API at the back end. And we should try to manage the uncertainty. So, for instance, this would mean that we would ask if the system is uncertain about what the user wants. Let's say that we have very similar probabilities for the slot food for two different values. Then we should probably ask which one the user wants. We should somehow follow the reasonable dialog structure. So like at the start of the dialog, we should say hello, and I don't know, if the user tells us something, we shouldn't be asking about it again, or things like that. And we should plan the actions towards the goal that we're trying to achieve. So, for instance, if we want the user to book a restaurant, we probably want to ask all the information we need for the booking, such as, I don't know, like how many people are coming. So basically, this is all that the policy should do, and there are few approaches that you can take, and like the most simple thing, or the simplest possible thing, is you can actually use some finite state machines. Essentially, your dialog state is the machine state there, and then this is good for like IVR systems, which means basically like you're talking to something on the phone, and basically not talking, just pressing options. So it's like this thing where you call up a bank, and it says something like, for account balance, please press 1, for money transfers, please press 2, for mortgages, please press 3, and then just deal with it via the menu. So that's actually also a dialog system, and you can use just finite state machines for the policy. The other option is like frame-based systems, or some kind of flowcharts like this. It's essentially trying to fill certain slots and provide information, or asking more questions, and essentially it's rule-based. It's kind of formalized rule-based. There's even this standard called voice XML, which is, I don't know, about 20 years old by now. So Probably like, you know, nothing like state of the art, but it's still there and it's still essentially usable. So that's like a rule-based way of doing that, or you can just like code basically any kind of code. What we did when we worked on this public transport information system was Python code, and we had like a huge spaghetti code of a lot of if then else clauses, and it worked pretty well. It's again just, you know, eventually was a bit hard to expand and a bit laborious. Otherwise, it was reasonably well working. Now, if you want to go, you know, with a statistical approach, the usual done thing here is reinforcement learning, which essentially, you know, we could say, okay, this is just a classifier, right? We just have a bunch of actions that we can take, and we want to pick the most likely action. So we're classifying out of a set of possible actions. However, if you just have like static data, static dialogues, you can you always see only one action taken at each point, because this is what happened in the dialogue at that step, and you see that I don't know, like this, the assistant. You know, if you look at let's say at these examples, you know, in this case, you know, the assistant asked about the day of travel, for instance. So that's you know, they provided the number of trains and they asked about the day of travel. However, at this point in the dialogue, there could have been other potentially reasonable actions, such as asking about the time of travel, or you know, just asking and not providing the number of trains. That you know, would be also like perfectly plausible, just saying, okay, what day would you like to travel? Or we could ask about the day of travel and the time, and in the same same sentence. These are all reasonable actions. But here, if we just train a policy from this data, we know that the only good action is providing the number of trains and then asking about the day. So this is not ideal, because we know that there are other possible actions. So reinforcement learning essentially allows us to make the system try out all the options and see which of these are good. So we can allow basically more correct actions at a given point. And again, reinforcement learning is looking at the overall reward. Yeah.
So I feel like the last approach, even if like it allows like more like exploration, there's so much more risk for error. And I feel like a lot of systems right now, even like Alexa or that, they're very like constrained. So I don't know if like there's any system that actually uses that where you can like have like a proper conversation.
Right. I would say there are. Yeah, it's a good question, because again, as I said, reinforcement learning, it's kind of hard to train, hard to get it to converge. There's quite a few research systems that are using reinforcement learning in this type of conversations, where you deal with this type of domains with stuff like booking restaurants or things like that. But you're right. It's a question whether this is actually used in deployed systems, where I would guess that most of them would have it would be LLM based, which is like a completely different story, and has some reinforcement learning to it, but not in this like formalized way, or it would be just rule based. So I'd say they're probably if you want to actually to actually train the system, then the reinforcement learning makes sense and gives you obvious advantages, as opposed to like training a supervised policy on like a static data set. But even though if the static data is large enough, you can probably do that, and you would be more or less okay. I mean, I've seen basically the reinforcement learning gives you like a few percent boost over like a supervised baseline in this case. So yeah, but you can, you know, these are kind of like reasons why we would want to do it. You know, conceptually it's better. It has definitely also some downsides. I just, you know, I'm not gonna go into much into reinforcement learning, even though it's like a huge area, and yeah, as you mentioned, it's not completely ideal anyway. But you can basically take some kind of reinforcement learning algorithm and directly let it drive a dialogue policy. Were you asking? Yeah.
Question for the previous one, also for dialogue tracking. Is it possible when you try to have a task-oriented single master system prompt, element-based?
Task-oriented. Can you?
Task-oriented because you showed us a task. For example, reserve as auto, right?
Right.
But only using LLM, and all that intents and then provide that in one big system prompt. Also
Right.
SQL maybe.
Right. I mean, I guess so. I think that you could try. I'm not sure how, you know, like how well it would work. But yeah, you could try that. I mean, I'll show an example of like a full system with LLMs. But yeah, we actually, which was an experiment that we did, and we actually split it up into several prompts. So it's kind of still kind of following the pipeline. It's just like using the same LLM with multiple prompts for different steps. But yeah, you could technically do that. You basically give all the instructions in the same prompt and see what the LLMs will do, and you could technically ask it to you know, produce chains of thought with like explicit steps and.
Or you mean that chaining, you meant first like taking the intent slots another in one prompt, then dialogue tracker to issue the SQL and get in another information, and then policy and action. Yeah,
basically, yeah. That's kind of what like what I will show in a few minutes. Yeah, basically, you can prompt like give specific prompts for specific steps to the LLM, and it kind of works, or you know, depends on the implementation, but it does. I mean, yeah, here I just wanted to mention, yeah, you can basically just run the reinforcement learning to train this dialogue policy or the action selection. However, usually you would need a so-called user simulator, which means that you build another dialogue system, usually like a rule-based one, but still you need to build a dialogue system to simulate the user, so you can train your policy. Because it's kind of the same idea as when you train the LLMs with the reward model. There you also you have a reward model instead of using people's feedback directly, because here again you need like thousands and thousands of dialogues to make the reinforcement learning actually converge. So what you would do is usually just have a you know, some kind of a user simulator, and usually you add also some kind of an error model that like simulates your speech recognizer noise or errors of the language understanding step, and then you can basically like run this with some kind of reinforcement learning algorithm such as deep Q networks or some kind of policy gradient algorithm to actually train the best policy. So that's just let's get rid of these the reinforcement learning and then the policy. So that's just as an example. Obviously, it's like much more complex than that usually. So now we're basically done with policy, and we'll try to look into language generation and response generation. And here I'll show a couple more approaches, especially because this is something that I'm mostly like interested in. So the idea of you know, the language generation or response generation step is essentially like the opposite of language understanding. So we have this dialogue action, or we have some kind of structured representation. So we can, you know, we can kind of take this a bit more general. You can say that we have some kind of data, and we want to represent them as natural language text. And you know, how we want to or how we express that might really depend on the context. And you know, we want to be probably want to be fluent. We probably want to avoid repetition and be natural and all this sort of stuff. But yeah, there might be some additional, like, you know, criteria that you want to follow. It really depends on what you're implementing. The traditional approach especially in dialogue systems, but in general, wherever, you know, you want to generate data onto text, is by using templates. So the idea here is that you just like have predefined templates. Someone needs to write a template like this, and it has placeholders for the individual slot values, and you can just feed in the the individual slot values and produce a sentence. This works pretty well for limited domains. And for instance, if you look at, you know, these virtual assistants like Alexa or Google Assistant, this is exactly what they're doing. They just fill in predefined templates. If you want to do it better, or do it, you know, do something more interesting with it, and maybe have like more varied replies, because this kind of gets repetitive, and obviously with larger domains it kind of gets tedious to build all those templates and combine the templates. And for instance, for our public transport information system, this was actually like combining the templates and putting them together to form the reply was actually the slowest step of it all. Basically, everything was like really blazing fast, but this gave us like, I don't know, like a 1 second lag for the responses, because there were too many templates essentially. So that's just you know, the rule-based version of that. And if you want to go with, you know, work with transformers, you can essentially just fine-tune the transformers. You can just feed in the feed in the data in some way. This is actually like a slightly different representation of the data. This is RDF triples, but it doesn't really matter. You can just like linearize the data and feed it into the model and have it generate the output text. So that's essentially just, you know, basically what the transformer would do. You could do this with a decoder model or encoder decoder. That doesn't really matter. The pre-trained language models are kind of good at implicit copying. So, you know, if you feed in this named entity, you don't need to really care about it being copied properly. It mostly will work reasonably well. So you can just do that. You can, if you want to like improve this, you can do this, like, you do beam search and then re-rank the outputs, basically like check the outputs for errors somehow. For instance, checking whether they actually contain the slot labels that you fed into the data, and then you can pick the output that has the least amount of errors. So that's kind of the basic approach, and this works reasonably well. Essentially, basically in 2020 there was like a shared task for these, basically specifically for this, for like generating text from RDF triples. So which are basically, you know, you have just subject, predicate, object, and you have a bunch of these triples and you want to generate descriptions based on that. And me and Zdeněk, who was my PhD student back then, so this paper, we wanted to build some kind of a fancy model, but then we just fine-tuned one of the pre-trained language models, and it worked so well that we just submitted that, and we did pretty well in the shared task. So there wasn't like much to do or to try out. It just worked more or less. In most cases, there's still the problem with hallucinations or with the outputs not being completely accurate. But as a baseline, as a system, it works pretty well. What specifically we then tried, and what other people were also looking into, was basically if you want the language models to be a little more accurate, if you want them to essentially stick to the data a little more, what we can do is basically combine this approach, just like generating outputs, and combine it with the templates. So the idea here is that we start with templates, start with like very simple templates for individual pieces, and what the language model is tasked with doing is only just put these templates together, just combine them in a single sentence or in a single piece of text that's kind of coherent. You can kind of see here that would you like to make a reservation at the restaurant? It is an expensive restaurant, its rating is 4. So the templates are really simple. So you don't need to write so many templates, because you just like write one piece of information each essentially. And you just feed it all to the language model, and you can see that it is able to combine it into like a reasonable sentence saying, okay, this is a expensive or a fancy restaurant with a 4-star rating, would you like me to reserve a table there? So that's kind of the idea, and you can even build a system that, and that's what we did, that it uses a lot of essentially open domain data, and then basically you just write these simple templates, and it will work pretty well, combining templates from different domains. Basically without no like in-domain training data, and you can actually also take like a prompted large language model instead of fine-tuning some pre-trained language model for it, and it will also work pretty well because LLMs are pretty good at just working with text. So we essentially just, instead of having this task of like data to text generation, what you kind of change it into is just text editing essentially, or combining several short texts, and this is something that the language models are pretty good at. So that's kind of a in between step before like just like going fully with LLMs. Where LLMs you can just feed LLMs some data, and if you feed them some JSON and prompt them, okay, your task is to write a nice sentence out of that, or a paragraph out of that. It kind of works, but there are still some issues, as in like when we tried it, when we played with it, we actually had to force the language model to produce this output so that we can actually get the response that we want. Otherwise, it would give us many different variations of the same, and it was kind of hard to parse out the output, for instance. And it's also kind of sensitive to the prompt. You can kind of see that there is a specific sentence saying please do not hallucinate, and it actually works. It actually has an effect on whether the language model hallucinates or not. So it's kind of it's again, it works pretty reasonably well. It's just kind of hard to control and use. Like with like the closed models, there's still issues of that. Like How do you replicate? How do you know that the language model hasn't seen the data? Because that's also what kind of like these guys found that basically if you if you take a benchmark and you look at the data and you feed it into the language model, it works really nicely. If you change up the data, if you, for instance, let's say that you take this sentence of this manor being in Ireland, and you change the name of the building, then you might get more errors in the output, because I assume that the data probably is, if you're feeding in fictional data, you get more errors essentially. That's the idea. So the language model still cannot fully kind of disengage the facts that they have seen during their pre-training and just use the data that you provide them in the prompt. So that's kind of the issue here. So that's like one option of doing that with LLMs. And like the essentially last option that I want to show is an experiment we tried. Basically, we know that LLMs are pretty good at writing code, right? So the idea was, okay, let's just take them and give them some examples and make them write templates. So that's essentially the idea. So we basically like have like LLM generated rules, and I mean this experiment is just with templates. We have some more recent experiments hopefully coming soon with some more complex structures, but here we just want them to like learn to write templates, and this essentially gives us the Python code for the templates, and we can check the code, we can see if it generates the correct outputs. If not, we can directly just fix bugs in the code as we would do if a person wrote it. And we can run the code on a CPU in like a fraction of time that it would take to run the GPU. So it works pretty well. On the other hand, so far this version is kind of not so good at generalizing to unseen data. So you really need to like feed it almost basically all the cases that you wanted to cover. Essentially, just it's like for limited domains it works. If you want to go broader, if you let's say would want it to generalize to a different domain, that's not really what it can do yet in this iteration, but we're looking into it. So that's kind of what we're playing with right now with like how do we force LLMs to be accurate, and one of the options that we see as quite plausible is just let them write code, and we can potentially fix the code if there's a problem, but we can exactly see how the final NLG system will behave. So yeah, so we basically covered the pipeline here. So we did basically all of these steps, and now I want to show basically approaches that just take all of this and try to do it with like a single neural model. So that's like the so-called end-to-end task-oriented approaches. And this, like with the separate models, we can say, okay, we're a bit more flexible. We can just, like let's say we want to retrain the NLG. And we can keep the rest of the modules. That's kind of a positive. It's also a bit more explainable than just getting the reply. We can also see which of these steps went wrong, for instance. On the other hand, let's say that like the NLU makes an error. That error propagates to the tracking, to the policy, and even though these models, these are perfectly fine and work completely correctly, we still get an error. So the errors kind of accumulate along the pipeline. So that's a bit of a problem. The other problem is that let's say that we improve, let's say we improve the NLU. In that case, And we might not actually get better results, better outputs, because if our policy is not able to make use of that improved NLU, then we just spent a lot of time improving NLU for absolutely no reason. So there's issues with like having too many components. So the idea is, okay, let's just have a single neural net to do everything. We can just like optimize it to produce the outputs. We can potentially like use reinforcement learning as well, but don't have to. And it will work. We will have like a single model to do everything. There are some problems with that. Basically, we will need a lot of data, especially like for the if you're not using LLMs, if you want to fine tune a model, we need a lot of data. And we kind of losing control of the output, so we will have hallucinations or more hallucinations than if we use, let's say, statistical NLG only. And the output also might still be repetitive, because that's kind of a less prominently shown problem of especially the smaller models, not that much LLMs. Is that they settle for like the most frequent phrasing for everything. And for instance, if you just try to train a transformer-based chatbot for chit-chat on some chit-chat dialogue data sets, you will get a model that will basically just respond with stuff like, I don't know, yes, no, I'm sorry. And basically with responses that are kind of dull and safe, and you can kind of respond to anything with these responses. Just because there's just too many possible replies with everything, and it's kind of hard to model that with softmax, which tends to prefer a single option. So you get like the most frequent outputs essentially. So that's just like a side remark here. But if we want to model task-oriented dialogues with a language model, what we would do, or what a lot of people did, and we also did some experiments on this, is basically you just prompt a language model with the dialogue history or with the user input. Again, we're just prompting, so we're ignoring the outputs. And then you auto-regressively, so it means that at some point you start with a dialog state token and you generate auto-regressively the dialog state. And the state is just some kind of representation. Here you can see it looks kind of like JSON. It's not exactly JSON, but it might be similar. Whatever string representation basically works. And at this point, when it finishes generating the dialog state, you can query the database. You can check based on the user preferences what the current state is, and usually we would just basically feed back the database output in terms of the number of results found in the database. Again, this is just prompting, so you're kind of like you can see that you're prompting here and you're prompting here, so you're kind of interleaving generation and prompting, and this is also something you can do perfectly well with transformer models. And then you generate the system output at the end. And here you can also see that it's delexicalized. So it's essentially you're generating a template where you can kind of fill in, for instance, this this value from the dialog state. So this is essentially like how you would do it before there were LLMs. You could basically fine-tune pre-trained language models such as GPT-2 to do this, and it works reasonably well, except for the issues that I mentioned. So there's some hallucinations. You need a lot of data to fine-tune it, and sometimes the outputs might be a little dull, if you look at, let's say, the human data and you look at the variability in terms of like how many different words it is using or what's the entropy or things like that, you will see that this will be like lower than expected for humans. But it will in most cases provide you with reasonable replies, and there are some extensions to make it a bit more accurate. So this is like a valid approach to generating dialogue responses with like a single network. You can obviously do the same thing with LLMs, but you would probably have to fine tune them to do that, or you can try to write like a single huge prompt that does this all. What we did, and what a bunch of other people also did, was basically we just tried to prompt the LLMs for the task and kind of do it in the similar way. So we basically, again, we need to get the dialog state, query the database, and then generate the response. So we have like two steps where the LLM is generating something. First it generates the dialog state, then it generates the response, and in between there's a step where we just ask the database, which is just like an SQL query. So it's kind of the same, but what we did was we added another step, which is like what domain the user is talking about. So are they talking about trains or are they talking about hotels? Because that means that this meant that we changed the prompts, or the prompts were different for each of the domains, and we played with the multi-was data set where we had like the 5 or 7 domains. So it wasn't a big deal writing these specific prompts, but it's just something to bear in mind that you might want to do, because in each case we knew which slots we are looking for in each domain. Whereas, if you did not know the slots, then the connection to the database would be very hard. So that's why we did it this way. And we had like a 0-shot or a few-shot setting where we had some examples that we had just a few examples, like by far not the whole data set. I think we had like 10 dialogues or something like that, and we could include these into the system. So the whole operation was basically we get the user utterance, and then we have an LLM prompted to detect a domain, basically to tell us which one of the few domains in the data set we're dealing with. Then we could potentially get these few shot examples that are infused in the prompt for the state tracking. So the state tracking is basically working with this kind of a prompt. Basically, we ask it to find all slots in the dialog, or the proper slot values. You can even see that it's mostly about like us telling it how to produce the output. You can see that there is a description of all the slots that we asked about, and potentially the examples. These are optional. Then we have the dialog history, and then we have the user input that was like the last step of the dialog at the end of the history. So this is what we fed to the LLM, and we get the dialog state that will tell us, okay, this person is looking for a 5-star hotel in the north, and we have these slot values, which means that we can query the database, get the number of results, and then we have another prompt for generating the response that produces the response. And you can see that it's kind of more or less the same approach that you saw in here. It's just that we split it into multiple prompts, and it's not fine-tuned. And this again works reasonably well. I would say we tried it basically with right after ChatGPT came out, and it kind of we had kind of mixed results. It wasn't so great for the state tracking, But there are some other papers that basically tried it a little later, tried a few more approaches, such as using SQL or using Python code to produce, instead of just telling like entity colon value, if you produce Python code that will kind of simulate something like I don't know, like find hotel and then say stars equals 5 and so on. So basically this kind of like fake Python function, it works actually better than this approach where we basically just tell it to get the value. So basically just tuning the prompts goes quite a long way. And now I believe this is like more or less state of the art, or this kind of approach is more or less state of the art for this. So that's basically how you would solve task-oriented dialogue with LLMs. Obviously, you're still dealing with a lot of issues, and it's still not working perfectly well. But it's kind of reasonable, and the main advantage of this is that you need much less, or potentially even like no data in the domain, and you have like a fully neural or fully statistical system. So you don't need to write rules, and you don't need to collect data, and it somehow works just based on the descriptions of the domains that you're working with. So that's kind of the task-oriented way, and I want to just mention one more thing here before I talk. One last thing that I want to talk about later is evaluation, but before then I want to just mention a thing that is kind of often used or used in production. If there is a production-based system that is task-oriented or like for a specific domain that is based on LLMs, it's usually just retrieval augmented generation or RAG, which means that basically you just feed some data that you retrieve from a database. So let's say that a company has some kind of a knowledge base, and based on the user question, you first retrieve stuff from the database, and then you feed it to some kind of a language model. It could be even like a fine-tuned, smaller model, but usually it would be an LLM, and this doesn't actually need any kind of a structure. So especially if this is just like a text-based information retrieval, you don't need specific slots or stuff like that. Obviously, the specificity of the information that you're getting might be compromised, but you're getting reasonable replies, and the LLMs are like good enough to produce like nice and fluent replies, and not just like copy the information. You might even like feed in more outputs, and the LLM is able to pick out the relevant information. And the retrieval might even be like optional if the set of information that you're working with is not so large. You might just feed everything in there and still be able to get the LLM to work with it, even though you might actually still want to do this, because even though the theoretical context windows of LLMs are really high, it's not completely certain that they're able to actually use all that context window effectively. So some pre-selection of the data still might improve the things. You might also want to ask, and this is what we tried in one experiment. Basically, if you first ask the LLM to see if the retrieved stuff is actually relevant at all, and if not, you might have some kind of a backup operation. Either tell the user that you don't know, or try to hallucinate something, or back off to some rule-based system or something like that. But so that's like another kind of alternative option to what I've just been talking about for an hour. That is actually also used in some production systems. Right. So this is kind of, trying to solve the dialogue response generation and looking at like general approaches to text generation. And now the last thing that I want to look into, and that kind of basically Ondřej prompted me into, because we're actually in my group we're actually doing a lot of evaluation and looking at a lot into evaluation approaches for text generation. I think it might be good to quickly mention some of that. So one thing, and that's basically the paper that Ondřej has plugged like 2 or 3 times already. There's a problem with like evaluating on benchmarks, and I kind of mentioned that a little bit with the NLG approaches. I'm not sure it's worth basically. With this issue with like the models kind of are able to produce outputs on the benchmark pretty well, but once you change it up a little and once you change the data, they're not so great. So that's the issue that like you never know what a language model has seen during training, and unless you have like completely new data, then you cannot know if the language model has seen the data. The other thing is that like the LLMs are kind of saturated or basically targeted to just a bunch of benchmarks, where everything every language model will get you a score on MMLU or GSM8K or these benchmarks. There's also not that much text generation in them, so they're just like generating a single phrase or a number or things like that. So it's not a great test for text generation either. And the main problem is that like a lot of these benchmarks are actually leaked into model training. And it's not just about pre-training. So it's not just about during the pre-training the model has seen the benchmark. It's also about a lot of people are basically pasting examples from benchmarks into ChatGPT's web interface, and based on OpenAI's policy, that means that OpenAI can use this data to improve their models. And this is, it might be, we tested this just for ChatGPT and basically looked at 200 over 200 papers that reported to usage of ChatGPT in the first about a year since it was deployed. And what we saw was like a whole bunch of benchmarks on various different tasks that have been basically either like just a few examples have been leaked as per the paper's reporting, or even like the whole benchmark was just passed to ChatGPT via the web interface, which means there is probably somewhere in OpenAI's improvement data. So you can never know like when that pops up in the LLM. So basically, like any kind of static benchmark that has been out for a while is kind of prone to this. The worst case was that when people like built their own benchmarks, and the first thing they did was feed it into the web interface, which meant that they just like leaked a completely new benchmark, which is kind of a waste of data. And by the way, with ChatGPT, if you use the API, if you don't use the web interface, the policy states that OpenAI will not use this data to improve their models. So apparently, like if you trust OpenAI not to use it, then it should be fine. But it's always a bit of a problem. So it's like it's always kind of better to evaluate on new data that the model kind of hasn't had a chance of seeing, and to get the data as cheaply as possible. So ideally without any annotation. So that's one thing with evaluation, and the other thing with evaluation, and this is also what Ondřej mentioned in the morning, is the type of metrics or how you evaluate or what you ask about. Obviously, like the standard thing that Ondřej said was showing for machine translation is blue scores. So basically, you just get a score based on some overlap with the reference. So you kind of, if you have some LLM output, you can compare it to a reference human output and see how much it matches up. You can kind of see that, if we have this data, let's say this is some data, and we feed it through an LLM and tell it to write a weather report, and you can kind of see that this is not a great weather report, right? But because sky will be mostly clear, not really, and this doesn't say anything about winds. So, but you can basically compare it to this human written, apparently correct reference, and you can get a blue score, something like this, right? So that's one option. The other option is you get some better, more fancy metrics based on some usually neural transformer models, and you can get something like, let's say, BERT score, which is based on BERT, and this is like essentially like embedding similarity of these two sentences under BERT's representation. So that's another option. Or you can ask an LLM, you can prompt an LLM to evaluate it for you. And you can say, okay, rate the factual accuracy on a scale of 1 to 10, let's say. And then the LLM might output something like this. And this is, again, like pretty good because you don't even need to have a human written reference. You can kind of see that it disappeared. So that's an improvement, right? Or you can give it to humans and ask them, is it accurate, yes or no, or give them Likert scales. Again, like 1 to 10 or 1 to 5 or something like that. This is all nice and well, but the problem is that you can only compare between, if you know that your blue score is 0.184, or if you know that, I don't know, like 66% is factually accurate, it's only good for comparing between systems. It doesn't tell you anything deeper. You don't know why your score is 0.184 or something like that. So this is a kind of a, it might not bother you, might be okay, but maybe you want a deeper insight, and that's what we were been experimenting with, and that's what Ondřej mentioned, because that's also what some other people have been experimenting with in machine translation, and that is error span annotation, which is basically instead of trying to assign some kind of a score, we want to basically just mark what's wrong with the text. Basically, just mark which parts of the text are wrong, like this. So in here you can see that this is essentially like incorrect because the skies will mostly not be clear, and we know that from the data. And the other thing, we don't know from the data, we don't know anything about it, so that's not checkable. So this is kind of a way of getting some more deeper insights, saying, okay, the LLM, I don't know, like hallucinates a lot or produces a lot of text that are not checkable, for instance. So we also can see for an output, we can see where the error is located. So we get a bit more detailed feedback, and we can still compare models based on how many errors per output they produce, for instance. So it still allows for comparing models, and we basically used this for some evaluation of LLMs, and based on that we actually built a tool that kind of simplifies this. So this is just like a plug. If you want to do this kind of annotation, basically error annotation, there's a tool called FactGenie that is on GitHub, and you can basically just define these categories of errors that you want to use. You can feed in various different data formats. I mean, we build this like customized visualization for weather, and you can do that too, but like, you know, JSONs and CSVs are just supported out of the box. And you can ask either humans or LLMs in like very similar setups, so you can easily feed the stuff to an LLM to classify, or you can create like a crowdsourcing campaign to classify it, or you can just like, you know, spread it in your group and do it like by yourself, and it all kind of works in a similar interface. And like the experiment that we've done with this is basically we just try to generate like weather reports and sports reports and stuff like that, basically on open data. So basically data unseen by the models, where we avoid this issue with the data leakage, because we just like collected the weather reports for the next 5 days at the time when we were producing the outputs. So the models can have seen the weather, for instance, or like, you know, recent sports events. Again, the models can have seen the events, so they must have gone by the data that they were given. And we used some open models that are like, you know, like 7-8 billion size, so like a moderately sized LLMs. And what we found was like 80% of the outputs had errors. So it depended on the domain, it depended on the model, but still like the vast majority of the outputs had errors. So there was quite some issue with the factual accuracy of the stuff. And it really depends on the data and if the model knows it or not, or how complex the data is. And, you know, the more complex the data, the more space for errors. So that's like one thing that we tried, and the other is some experiments with basically trying to basically formalize this and make this a bit more general, and basically use this approach for evaluation with LLMs. So we basically get any kind of text, any kind of generated stuff, and then we basically have different evaluation aspects, and it could be accuracy, but it could also be some other things like fluency, or I don't know, adherence to desired sentiment or stuff like that. Here the examples is for conciseness, so we, you know, evaluate how much the answer is to the point. And we basically just prompted a whole bunch of, so we don't have just one LLM, we have an ensemble of like 5 of them, and then one LLM to aggregate the results. And we basically are able to produce all the like error spans, so it marks the error spans like this. It gives us an explanation to why it marked each of the error spans as an error, and it also gives an overall score based on these error spans. And we basically compared this to some closed LLMs or some previous metrics using closed LLMs, and we're kind of on par with them. And we also provide a bit more explanation, or like a bit more detailed annotation than these other models. So this is also like a way of, you know, not just giving the error spans, but also forcing the LLMs to explain, which is what we do here. Right. So that's basically what I wanted to show. I would say, like, to conclude, yeah, there are useful and very, very helpful systems, but I would say like a lot of the tasks that we're dealing with are kind of far from solved. And the reliability is arguably the biggest issue. And there's a lot of things that I did not talk about and that you could look into in terms of like around dialogue and generation. There are like fully audio-based models inside like a single LLM. There's some incremental approaches that try to like start processing as soon as the user starts speaking. There are some approaches where you want to like analyze a lot of data, a lot of some recordings, and build like a chatbot, like a whole chatbot based on analyzed data. and there's also some research on trying to like reply and be a bit more adaptive based on the context on basically on linguistic grounds to the speaker. Okay. Otherwise, that's basically all that I wanted to say. So thanks for listening and thanks for bearing with me all the way to the end. And I guess if you want to discuss something or ask something, now's the time. Okay.
Any other questions?
I guess it's. Yeah, you have a question?
How do you value the LLM as a judge metric of prompting? Because every prompt for LLM can change, right? Every model has its own structure, and people do majority prompting. How to do metric evaluation based on that?
You mean how to evaluate metrics or how to evaluate?
Evaluate the performance of the dialogue system.
Right. I mean, usually, and this is also what we did in this experiment. You would basically get some data that was also evaluated by humans, and you just like check for correlations between the scores assigned by the metric and the scores assigned by people, which is. It's a bit of an issue. Like for instance, like for these explanations, we basically had to just manually, just like sample a couple, like a bunch of these explanations, and just look manually and check how a large percentage of these are correct. But for like the overall scores that the LLM would assign, you can just measure the correlations on some human annotated data. But you need the human annotated data. But there are some data sets that have human ratings and are publicly available, so you can do that. Okay. Any other comments or questions? If not, then I guess thanks.
Thank you very much.
Enjoy the weekend and the rest of the workshop.
Come back and visit us whenever you want.